Hi there, Physics 11, and welcome to your notes for May 5th to May 8th. So just to recap, last week we talked about Newton's first law, where we stated that an object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an external net force. Okay. Now that leads us to our second law that we have here, is that an unbalanced force results in an acceleration. Okay, so we use this unbalanced force. We're going to state that as this F net, right? The net force equals our mass times acceleration, right? So if we have an acceleration on our mass, then we have to have some sort of a net force. Or if we have a net force, then we've got to have some sort of acceleration on that mass. Okay. Now this is very similar to the one that we dealt with last week, where we're talking about the difference between mass and weight. Okay, or we had the Fg, the force of gravity, equals the mass times that acceleration due to gravity. So now we're just going to go for that overall understanding of what force is just mass times an acceleration. Okay, now that can depend on whatever that acceleration is, whether that's gravity, somebody pushing on something, any sort of thing like that. Okay, that's going to be, we're looking for this F net. And once again, I just want to remind you that our force units are newtons, and that is just kilograms times meters per second squared, right? And so that's if we're looking up here, our mass is in kilograms and our acceleration is in meters per second squared, which is how we get to these units. Okay. Now, something else that we're going to be talking about today, and you've got lots of questions on, is known as free body diagrams. Okay. So, a free body diagram. Okay, sometimes shortened down to an FBD. Okay, free body diagram. These are essential for most physics problems, both in this grade, next year in grade 12, and beyond. Okay, you're going to want to make sure you understand these. And a lot of times these are pretty straightforward. We're going to take whatever object we're talking about, and we're just going to draw it as a box. And then what forces do we have acting on this? Well, we know that we've got the force of gravity that's going to pull something down. If this object was sitting on a flat surface, then maybe we would have the normal force. Okay, that's the force of the table pushing back up on this, or the whatever the surface it's sitting on pushing back on. And then let's say somebody comes and pushes it from the side. Well, then we're going to have that applied force going in this direction. And later on, we're going to get to the point next week where we're going to be talking about the force of friction. And if I'm pushing something this direction, friction is slowing it down, and going to be something like that. So my free body diagram here is just taking my object, and then I'm going to apply any of my forces that might be on here. Okay. Now, some other versions of this might be if we had, say, a pulley. Okay, and on this pulley, we have two masses. Well, I've got the force of gravity pulling down on this one object. Okay, I've got a force of gravity 2 pulling down on this object. And then I've got the force of the rope pulling this up, and we call that our force of tension. Okay, the tension on the rope between these two objects. Okay, another type of situation we might have is if we're talking about something on an inclined plane. Okay, we've got this object here. Once again, we have force of gravity. And the reason why we're not dealing with these inclined planes in this first forces unit is because we're also then going to have these angled forces in here. But we've got gravity pulling down, we've got the normal force pushing up. Maybe there's a person pushing this up the ramp as well, right? They're just pushing this up the ramp. And that's why we use these inclined planes, make our jobs easier. So these are all just examples of free body diagrams, okay? Almost any word problem you have, almost any physics problem you have from here on out, you're going to be drawing these free body diagrams and labeling all of your forces on them. Okay. You've also got a worksheet on there where you're going to be taking some free body diagrams to understand what's going on. Okay. And we'll get some practice doing all of these today. Okay, we'll try some of these. All right. So, first question you have on here in the example section is a 5 kilogram block is pushed to the right along a frictionless track with a force of 10 newtons. What is its acceleration? All right. All right, we have our object, okay? We have a force of gravity pulling this object down. It's on a flat track, frictionless track, so that means we've got our normal force holding it in place, okay? Now, our normal force and our gravity force, these are going to cancel each other out, right? We can consider, say, this pen sitting on this table. Okay, the force of gravity is pulling it down, but it's not accelerating down because the table itself is also exerting a force back on the pen to keep it in place. Okay, so pretty much anytime we're talking about a flat horizontal surface with an object sitting on top of it, gravity is pulling it down, whereas the normal force is pushing it back up. And if that table is stationary, if that pen is stationary, then those two balance each other and cancel out. The next thing we on here is saying is pushed with a force. So I'm just going to draw it this way, and I'm going to call that my FA, my force applied. And this is 10 newtons. Okay. Now, we want to know the acceleration. So if we're looking here, we're going to say that the F net equals mass times acceleration. In this situation, this is the only net force I have because the force normal and the force of gravity cancel each other out. So this is going to be my 10 newtons equals my 5 kilograms multiplied by my acceleration. Well, I'm just going to divide out that 5 kilograms from both sides, and I get my acceleration is 2.0 meters per second squared. Okay, so we start off with our free body diagram to make sure that we had everything in place. We wrote out our formula, we substituted the information we had, and then we solved that same situation. Okay. I can get room to do the second example on here. We've got a 650 kilogram car accelerates at 4 meters per second squared south. All right. Maybe it's more of an SUV or a station wagon than a car, but hey, that works. And usually, like I said, usually we draw these as a box, but if it's something simple to draw, you can draw as a car, or you can draw this as a box. It doesn't really matter. We just want to make sure we have all of our things acting on it here. And so we have the force of gravity pulling down. We have our normal force pushing up. The car is stationary. Vertically it's stationary. We're just dealing with a horizontal. And then we've got an acceleration coming out the front here. All right, so now we just need to figure out then our net force is whatever's causing this to go forward, and that's all we're looking at. So in this case, F net, again, equals mass times acceleration. Our mass given from the problem is 650 kilograms. Our acceleration was given to us as 4 meters per second squared. Okay, and so we just multiply these out and we get 2,600 newtons. Okay, force is also a vector. Okay, so we should include our direction, and since our acceleration was towards the south, then our direction here is also to the south. Okay? So 2 types of problems, both want to just include very similar processes. Let's draw a picture listing out any of our forces that are on here. This is that free body diagram. Figure out our formula for now. Mostly we're just dealing with these. And then substitute our values and then solve, making sure we put our final answers to correct sig figs. And I should correct this, this was 5.0. So we have 2 sig figs here, and we have our 2 sig figs in this answer. Okay. Now, let's move on to our third example. A 1,500 kilogram ice cream truck accelerates from rest to a top speed of 45 kilometers per hour in 8.0 seconds. Okay. Okay. Kind of looks like an ice cream truck, maybe. Flat surface, or doesn't say anything about an angled surface, so we're going to assume it's a flat surface. We're not worried about any friction as of right now. Okay, so all we got is just whatever this force is going to be in that driving in that first direction. But we did have force of gravity and normal force, and then we've got the applied force of the engine on this vehicle. Now, it wants to know what is the net force acting on this vehicle. Okay, so we need to know our mass and our acceleration. And based on the problem, we have our mass in kilograms, 1,500 kilograms. Accelerates from rest. Okay, so we want to remember that that's our V initial here is 0 meters per second. Comes to a top speed, so our V final is 45 kilometers per hour, and it can do this acceleration in a time of 8.0 seconds. Okay, now we've got a problem though. I can't figure out my acceleration because remember our units here were kilograms times meters per second squared. I have my kilograms, but my velocity here is in kilometers per hour. Okay, so I need to make my adjustment, and that means I need to divide by 3.6 to convert this to 12.5 meters per second. Okay, so we just want to make sure we are carrying extra values, or sorry, extra decimal places in here. Okay. Until we get to our final answer, and then we can round those off. Okay, now I have my mass, I have my final velocity, I have my time, but I still don't quite have my acceleration. Okay, so we need to reevaluate our formulas here, and we got to pay attention to that last unit that we dealt with, where we could say V final equals V initial plus AT, which, since we're looking for our acceleration, V final minus V initial divided by time equals acceleration. So 12.5 divided, or minus 0 divided by 8. Okay, this gives me 1.5625 meters per second squared. Okay, once again, carrying those extra sig figs to do my final answer. I'm going to take those values now. I can say 1,500 times 1.5625. Okay, and so 1,500 times that 1.5625, I get 2,343 newtons. Go back to the initial problem. We had 2 sig figs, 2 sig figs, 2 sig figs. So we can say that the net force was approximately 2,300 newtons. Okay, so these are the style of problems that we're going to see. Not only are we going to have those straight calculation and substitution problems, but we're going to have other ones where we've got to use those earlier kinematics equations to help solve these problems. Okay, so make sure that we still remember those. We've got those with us when we're doing these problems. Make sure that we understand how to go back and forth. If we're having difficulties with those questions, please make sure you post those questions onto our website and I can attack those later on. Okay, now, 2 last examples on this page. We've got Stan and Kyle are pushing a 75 kilogram sled along a frictionless ice rink. Stan pushes with 55 newtons, Kyle pushes with 45 newtons. Find the sled's acceleration. Okay, so we've got this little note here to find F net. Now it says when 2 forces, we can just say when any number of forces work together. Okay, so to find the F net when forces work together, the answer to this one, add them up. Okay, just want to add those up. Okay, now beside that in there, we also say to find when F is when many forces act on an object. Okay, so we could also say then that this is when they're working together. When forces aren't working together, okay, for this one, we're going to say that the F net force is going to equal the winner's force minus the loser's force. Okay, we're going to come back to that one in a second when we talk about the Batmobile. Okay, but these 2 boxes here, these are going to be very helpful. When forces are working together, we add them up. When forces are working against each other, okay, whoever has the stronger force is going to win that situation, and so then it's the winner's force minus the loser's force. Okay, so this is when people are working in opposite directions. Okay, we'll come back to this part here when we talk about the Batmobile, like I said. Okay, so let's go back to our Stan and Kyle pushing their 75 kilogram sled. Okay, so we have F net. Okay, we're going to add these up. So let's say it's the force of Stan plus the force of Kyle is going to equal the mass times acceleration. All right, let's plug in some values here. We know that Stan can push with a force of 55 newtons. Okay, Kyle can push with a force of 45 newtons. That equals our 75 kilograms multiplied by the acceleration. So our acceleration is then going to be these forces divided by the mass, or 100 newtons divided by 75 kilograms is equal to 1.333 repeating meters per second squared. Remember our sig figs, everything in this problem had 2 sig figs, so our answer should be 1.3 meters per second squared is the acceleration of our sled. Okay. Now we can use, or if we look at this next question, we're looking at Batmobile exerts a force of 8.5 times 10 to the 3 newtons. Friction pulls back with a force of 1,500 newtons and has a mass of 1,250. What is acceleration? Eventually you will be, actually probably starting next week, you will be calculating the force of friction, and we'll talk more about how to figure out that force of friction. For now, I'll give it to you as a value. Okay. We're also not going to calculate air resistance, but I could say there's air resistance in a problem. And essentially there we're just talking again, just friction or force that's counteracting whatever force we're looking at. Okay. Now, we said that our F net is our winners minus our losers. So F net is going to equal, now we've got to decide here. We've got a force of the Batmobile and a force of friction. And if we look at it, our force of our Batmobile is 8,500 newtons. Well, friction is only 1,500 newtons. So that means we're going to have the force of the Batmobile minus the force of friction. And we'll just do the FF for the friction. And now that will equal the mass of the Batmobile multiplied by its acceleration. And this acceleration is what we're looking for. Okay. In the last problem, I plugged in the numbers and then manipulated the formula. And this one, I'm going to manipulate the formula first. I've got to divide out this m on both sides. So what I'm going to have is my acceleration is going to be the F of the Batmobile minus the force of friction divided by the mass. Now we can plug in those numbers. Right? 8,500 newtons minus 1,500 newtons divided by our mass of 1,250 kilograms. Okay. Now you'll notice in this problem too, I'm not putting in any of the units. That's because from the get-go, all of the units are where we need them to be. So I know that my answer, because I had newtons, and kilograms, my answer is going to be meters per second squared for the acceleration. Plugging in these values, I get an acceleration of 5.6 meters per second squared. And that's already taken care of the sig figs for us, but we want to pay attention to the direction that was given to us, and so that is east. Okay. So since these are vectors and we should be including our direction, I guess we should go back and look at Stan and Kyle and say that they have 1.3 meters per second squared forward, because there's no actual direction provided for us. And so just let's fill in that as forward. Whereas the Batmobile, we were told that it's moving to the east. Let's make sure we put in that acceleration to the east. All right, folks, we're looking here at this next worksheet. I want to work through one of these examples for you so you're used to seeing these free body diagrams and how we're going to work about doing these. Okay. Since we have vectors, we want to pay attention to our directions here. Okay, so let's see, I've got an Fn equals 100 newtons. I have an Fg of 100 newtons. I'm also told that I have an applied force of 20 newtons, and I have a force of friction of 20 newtons. Okay, so when I'm looking for my F net, this is the sum of all forces. Okay, now if I'm looking at my vertical, my normal force is 100, my force of gravity is 100. They're in opposite directions. So one would be positive, one would be negative, and they just cancel each other out. Okay? Same as when I'm looking at my applied force going in this direction at 20 newtons, and my force of friction is pulling it back at 20 newtons, it's not moving. Okay? It's like me pushing this table. Okay? The force of gravity is pulling down with 100, but the force of the floor is pushing up with 100 newtons. So they cancel each other out. I'm applying a force to the right of 20 newtons, but because it's on the carpet, there's an excessive friction that's pushing backwards at 20 newtons. That means my object isn't moving, and I have a net force of 0 newtons. Okay? So we always want to make sure that we're putting in some sort of a directional thing in here, okay? Whether that's up, down, left, right, something so that we just have an understanding of what direction this net force is going to be in. For now, there should only be one direction or the other, okay? Either up, down, or left, right, okay? We're not going to deal with the multiple dimensions until next unit. Okay, so that was for the top 6 problems. Let's take a look at the second set here on this page. Okay, we are asked to find the missing blanks. All right, now I do believe there's a typo on this page, but let's take a look at this here. We have a block F normal, F of gravity. We have an F applied. We have a force of friction. Now, our F applied is 70 newtons. Our force of friction is 20 newtons. We're told we have a mass of 5 kilograms. And we are trying to find the acceleration of this object. Okay. Now, FG, this is mg. Okay, and so for this problem, I think it says 300, which is wrong. We would do our 5 times our 9.81, and we end up with approximately 49 newtons. And since this object is not going to be moving up or down, the force of gravity and the force of normal are the same, and so we'll say again 49 newtons. Okay. So then we want to look at our F net. And this object is not moving in the vertical, it's moving in the horizontal. So we have our winning force, the F applied, minus the loser, the force of friction. And that gives us a 70 minus 20, or a force of 50 newtons. So when we come back here to solve for our acceleration, remembering our F net is mass times acceleration. So our acceleration is what we're looking for, is going to be our F net, our 50 newtons, divided by our mass of 5 kilograms, and we end up with a value of 10 meters per second squared. Okay, so all that should help you get through that second page, right? All right, at the top of the third page, we have this little chart like this. We just want to kind of talk about these different forces that we can experience, or that we might see as we go throughout this course. Now, I've already talked about a couple. We have, sorry, switch colors. We have the F sub G. Okay, and this is just your force of gravity. We have the FAPP. Okay, so this is an applied force. All right, that's an applied force, and that's a push or pull. Right, we mentioned that's how we defined a force in the first place, so any push or pull would be the F applied. We talked about this F. Okay, this is the force of friction. Okay. This is against the motion, right? So we'll talk about force of friction, you know, the pushback of an object as it moves across the table. The rougher the surface, the more friction you'll have. Okay, and it always opposes motion. Okay. Another one we've talked about here is the Fn. This is the normal force. Okay. Sometimes described as the supporting force. Okay, it's the force of an object or of a surface supporting up whatever gravity is trying to pull down. Okay. Let's see, what else have I mentioned here? Oh, we've talked about this F air. Okay, this is air resistance. Now you mentioned, you'll remember that back in class I told you that you're not going to have to calculate air resistance. It's a very complex way to do it on any shape that's not nicely spherical or anything like that. Okay, so usually what's going to happen is we're going to provide you with some sort of an air resistance. And again, it's very similar to the force of friction. It's opposing the motion. It's against the motion that we're usually going with. Okay. Other than that, we've got two different types to talk about here left. We've got our T, or sometimes our F sub T. Okay. This is tension. Okay. And so for tension, we're usually talking about forces along a rope. Okay, so this will come into play when we're talking about pulley problems, or if we're talking about a tug of war, or if I've got a box attached to a rope and I'm pulling that. Okay, there's the force along that rope, and that's that tension. Okay. And then the last one that I'm not sure if we'll get to this course, but we might. We're going to call that FE. Okay. And this is the elastic force. Oops. Sorry here. Elastic force. Okay. Now, even though it says elastic, we're not just talking about elastic or rubber bands. We could also be talking about springs, okay, or anything similar. Okay, so that's the majority of the different types of forces that we're going to deal with in this course. Okay. Once again, now we're going to be talking about, we want to draw some free body diagrams. That's essentially what this whole page is all about. Okay, and so we want to apply these different forces onto our free body diagrams. So we've seen them in play on the previous worksheet where we're given the free body diagrams and have to list out and find out the information. Whereas this page here now is all about having to draw our free body diagrams. Okay. So for example, 1, a box is pushed across a rough floor with constant velocity. Okay, so we got to talk about this here. Constant velocity means no acceleration. No acceleration means that F net is also going to be 0 newtons. Okay, so when we go to draw our free body diagram, that means that our force of gravity, so dot in the middle so we keep that organized here, and then the normal force, I'm going to draw little lines on there because those two are equal. Equal and opposite in direction because we have no net force in the vertical. Okay, we're also saying that we're pushing this across a rough floor. Okay, so that means we're going to have an applied force. And the fact that it's a rough floor means it's not frictionless. We're going to have a force of friction here. Okay. Drew that a little bit too big. We want to try and make them about the same size because if we have 0 acceleration and 0 net force, that means just like our normal and our gravity had the same magnitude, our force of friction and our force applied must have that same magnitude. Okay. Now we're not saying that this option is motionless. We're just saying that it has 0 acceleration, right? Because forces are mass times acceleration. Without acceleration, the object's just going to be, it can still move, just no speeding up, no force. Okay. Example 2, a hockey player glides on a frictionless ice at a constant velocity. Okay. Again, we're looking at this constant velocity, so no acceleration, which means no net force. Okay, So let's draw our free body diagram. Okay. Once again, we're just simplifying our object, in this case a hockey player, as a square, as a box. We have our force of gravity pulling down. We have our normal force pushing up. Those are the same magnitude. Now we're saying we have a frictionless surface. So that means there's no force of friction, but if we're maintaining a constant velocity, that must mean there's no applied force. And so this then would be our free body diagram for this situation. The object is gliding, so that means no applied force, and it's frictionless, so there's no force of friction. These are the two free body diagrams to help us through that third page. Okay, so hopefully that helps you out with those first few pages and our idea here of Newton's second law, talking about unbalanced forces causing acceleration. Okay, you have a total of the 1 notes page and 3 worksheets to work through. Okay, hopefully you get all those. Any questions that you have, please post those on our website and I will get back to you on those as soon as possible. Thanks. Be safe, stay healthy.